Hi, welcome to Unit 8, Day 1. This is Part 3, where we're going to look at the ionization of acids and bases. Ionization of acids and bases, you can also think of that as what happens when an acid and base is put into water. So in general, what happens when stuff dissolves? Remember, there are two things that can happen if something is soluble in water, if it can dissolve. Electrolytes, things like ionic compounds, they'll break apart or dissociate into ions. Ions are anything with a charge. We call that process of breaking apart into ions ionize. So they will ionize. Non-electrolytes, something like sugar, will break down into smaller pieces, but they do not dissociate into ions, right? So you go from a clump of sugar that has, let's say, billions and billions of sugar molecules sort of loosely connects together into a bunch of those billion sugar molecules sort of dispersed in the water. So non-electrolytes breaks into smaller pieces, but no ions. Electrolytes ionize into ions or charged particles. Now, acids and metal hydroxide bases are electrolytes. So when you dissolve them in water, they break apart into ions. And if you remember about properties of different substances, one of the reasons why we had to know if a covalent molecule was an acid is because if covalent molecule is an acid, it will ionize and it will be lit, so it will conduct in aqueous solution. And this is sort of bringing that back. So why is it important to know what happens in water? Well, it kind of goes back to our definition of an acid and base. So remember, for an alkeneous acid, an acid releases H+, and it releases that when it's dissolved in water. So let's take, for example, if we have something like HCl, which is an acid. If you put HCl in water, what will happen is it will split apart into H+ and Cl-. So a couple of things that you want to note here in terms of the splitting. The acidic proton, or hydrogen, will have a positive charge, and then the anion will have a negative charge. Now, in this case, since it's one H+, and then there's just one Cl-, they'll both have a +1 and -1 charge. So in terms of writing this as a chemical reaction, we can sort of write it this way, where we start with HCl, and it breaks apart to H+ and Cl-. We can simplify that in this chemical equation here. So one thing that's important in a balanced chemical equation, not just the atoms, but the charges also must balance. So when you're doing your ionization reactions, for example, notice how on the left side, the overall charge is 0. There's no charges there. On the right side, you have a +1 charge and a -1 charge. If you add those together, they will give you 0. So the charges must balance on both sides. All right, let's take a look at another example of an arrhenius acid. So remember, an arrhenius acid releases H+ when dissolved in water. So if we take something like nitric acid, HNO3, and we put it in water, it's going to break apart into H+ and then nitrate, NO3-. So one thing that's important to see here is that for polyatomics, they just stay together as a group, okay? So we're not breaking the nitrogen and oxygen down into separate atoms as well. They stay together as a group, and the only thing you're doing is you're breaking the H+ off of the rest of the acid, right? So we can represent it this way, where we're starting with nitric acid breaking apart to H+ and nitrate ion, or we can represent it this way. And once again, it's important to know that in a balanced equation, the charges will be balanced on both sides. All right, what about bases? So for bases, they release OH- when dissolved in water. So if we take something like sodium hydroxide, it's a metal hydroxide. Sodium is a metal, OH is a hydroxide. If we put that in water, it breaks apart into Na+ and OH-. So remember, the metals are cations. They would have a positive charge, and then the nonmetals will have a negative charge. Now, hydroxide is a polyatomic ion, and its formula is OH-. You should know that, because that's going to be something that's super important when it comes to acids and bases. So hydroxide, you should know that it's OH-. Anyway, so we can represent it this way. We have sodium hydroxide on the left side, and I'm going to pause for a second here. Sorry, I just had to change the phase of the base. So ionic compounds before putting them in water will be solids. But anyway, so you have your sodium hydroxide that breaks apart into the sodium cation, Na+, and then OH-. Again, we can represent it this way. And once again, the charges must be balanced on both sides. So if you have an overall 0 charge on the left side, then you must have an overall 0 charge on the right side. And +1 and -1 together will give you a 0 charge. Let's take a look at another example of an Arrhenius base. This is calcium hydroxide. So we take our calcium hydroxide, if we put that in water, it'll break apart into Ca2+ and 2 OH minuses. And again, it's important to know that the charges are balanced on both sides. So on the left side, the overall charge is 0. And on the right side, the overall charge is 0 because you have a +2 charge and you have 2 -1 charges. Since you have 2 hydroxides, each with a -1 charge, that gives you an overall -2 charge from the hydroxides, and then the +2 charge from the calcium. +2 and -2 together gives you 0. So one thing that I wanted to note, now that we sort of see what happens when a base is dissolved in water and how it releases those hydroxides, is that the charges on the metallic cation matches the number of hydroxides. Remember how with an acid, the number of hydrogens would match the charge on the anion? Well, same thing is sort of happening here, where the number of hydroxide would match the charge on the metal. And that's because for an ionic compound, the overall charge must be 0, right? Balance is super important in chemistry, as you can see. So if you look at an example here where we have a metallic cation Na+, the number of hydroxides it would have for its base will be 1. Each hydroxide has a -1 charge. So NaOH. For calcium 2+, because it has a +2 charge, it should have 2 hydroxides. And then for aluminum 3+, it will have 3 hydroxides because its charge is +3. All right, so why don't you try using that knowledge for this? An unknown base has a formula MOH2. Okay, so it has 2 hydroxide. What is the charge on the metal in this base? Pause the video now, and when you press play again, the answer will be revealed. Great, the answer is +2. So remember, the number of hydroxides will equal the charge on the metal, and it has to be a positive charge, by the way. Okay, so let's go back to our sort of like summarizing this definition of acids and bases and seeing that, and when we dissolve an acid and base in water, what happens? So for acids, when you dissolve them in water, they break apart and they form H+. So they release H+ into the solution. Whereas with bases, when you dissolve them in water, they release the OH-. Now for these examples that we see here, for these Arrhenius examples, it's clear to see where the H is coming from in the acid and where the OH- is coming from in the base. But what about amine? NH3 is also a base. Where is that hydroxide coming from? So what this is proving to you is that you can't see the OH in the amine because it's not there. But what this shows is that Arrhenius definition is limited. It can describe many acids and the metal hydroxide bases, but it doesn't describe the amine bases, the NH3s, for example. So we need another definition for this amine. So since we can't define amine by the Arrhenius definition, we use what's called the BronstedLowry definition for amines, like what makes an amine a base. So in a BronstedLowry definition, the acid is a proton donor. So during a reaction, it will donate a proton. And the base is a proton acceptor. So it will take a proton from something during a reaction. Now, one thing to note is that many acids are both BronstedLowry and Arrhenius acids and bases. But in the case of amine, it only fits in the BronstedLowry category. So let's take a look at what does that mean for an amine, right? So what happens, how does an amine produce this hydroxide by reacting with water? So here you have your amine. This is ammonia. This is what's used in cleaning. So this is cleaning ammonia. And you have NH3, and then you have water. So I wrote it this way just to see it's a little bit easier. So remember how the water has an acidic proton, and it also has a hydroxide part as well, right? So this ammonia is going to take the hydrogen off, the acidic hydrogen, off of water. And when it does that, it forms ammonium, NH4+. There's 4 hydrogens here all together. And also hydroxide. So what's happening here is this water splits apart into H+. The H+ goes with the NH3, and OH- goes off on its own. So when amine is dumped into water, it produces the OH, the hydroxide, by reacting with the water, according to this Bronsted-Lowry definition. And therefore, that's what makes an amine a base. And you can also see it written this way. This sort of summarizes what happened. All right, so let's just sort of summarize acids and bases here, some of the things that we've learned about acids and bases. Important to note, acids, H in the front, Q in the back. That's how you can recognize them from their formula. Examples like HCl, H2S, HNO3, you can see the hydrogen in the front. And then something like vinegar, CH3COOH, you can see the Q in the back. Bases, on the other hand, they're metal hydroxides and amines. So example of metal hydroxides would be sodium hydroxide, calcium hydroxide. You have a metal, and then you have an OH minus, which is your hydroxide. And then you have amine, something like NH3. So nitrogen with three things that are, and those things can be either hydrogens or hydrocarbons, carbon-hydrogen molecules or pieces connected to the nitrogen. Now, what makes something an acid? An acid produces H plus when dissolved in water. So when you put acids, if there's an acid in the water, the amount of H plus is going to go up because it's going to make H plus. Whereas bases, they're going to produce or release OH minus when dissolved in water. So that's pretty much the main things that you need to know in terms of acids and bases, and defining them and recognizing them and identifying them. All right. Here's our next CFU. A substance is dissolved in water and produces OH minus. This substance could be, select all that apply. So go ahead and pause the video now. When you press play again, the answer will be revealed. All right, as we know, bases are the things that produce OH minus when dissolved in water. The first two are not examples of base. So methanol is not a base. It has a OH group, but it's not a metal OH. And then the next one, that's vinegar, CH3COOH. This is a Q group. The last two are bases. You have a metal hydroxide, aluminum hydroxide, and then you have ammonia, NH3. All right, which of the following shows what happens when perchloric acid is dissolved in water? So we have HClO4. What happens when it dissolves in water? What would that look like? Pause the video now. When you press play again, the answer will be revealed. All right, the answer is choice B. So remember, it splits apart in, first of all, you're going to find the acidic proton, which will usually be in the front, unless it's a Q group. And you sort of split it there, forming H+, and then whatever is left, ClO4-. And remember that you can figure out the charge on your anion because the overall charge on the right side must be 0. So if you have one H+, then you should have a -1 charge there. All right, that is it for part 3. The next will be part 4.